Yes, bear with me. We're doing 16.3 today, and we're going to be talking about the second and third laws of thermodynamics. After this video, you should be able to state and explain the second and third laws of thermodynamics and calculate the entropy changes for phase transitions. Alright, so the second law of thermodynamics states that for any spontaneous process, the entropy of the universe increases. So that means basically for any reaction that occurs spontaneously, the sign for delta S has to be positive, or delta S has to be greater than 0. Okay, so for spontaneous reactions, delta S of the universe must be greater than 0. If it's less than 0, then you have a non-spontaneous process. If it's equal to 0, then you have a process that is at equilibrium. So processes that increase the entropy of the universe occur spontaneously. Entropy is the state function. Again, that just means that you're looking at the delta S of your final products versus delta S of your initial reactants and taking the difference between the two. So we've been talking about systems and surroundings. Again, this is a recap of 101 when you were first introduced to thermodynamics. The system is the part of, is the reaction that you're looking at. So it's what you're observing. And then the surroundings is everything that's outside of that system. And the sum of both is equal to the delta S of the universe. Okay, so delta S of my system plus delta S of my surroundings is equal to delta S of the universe. So we know that in order for delta S of the universe to be greater than 1, right, because we just said that delta S of the universe is greater than 1, greater than 0 for spontaneous reactions, right? So we have S of the universe is equal to S of the system plus S of the surroundings, right? So we know that in order for delta S of the universe, or S of the universe, to be greater than 0, the sum of the system and the surroundings has to also be greater than 0. And so we know that whatever happens to the system, the equal and opposite happens to the universe, basically, when we're talking about change in energy. So if I have a system, for example, and if you go back to when I had that pool table, right? So we had the pool table, and you hit a ball with 5 kilojoules of energy, and only 3 is transferred to the other ball. Well, the other 2 kilojoules of energy went into the table in the form of friction. So that should sound a little bit familiar. So the system, which was the cue ball, right, lost its energy. It lost 5 kilojoules of energy into the surroundings, 2 into the table, and then 3 into the other ball. And so in order for that process or chemical process to be spontaneous, delta S, the total value of delta S of the universe is going to have to be greater than 0. And so how do we calculate delta S of the surroundings? So basically we take the negative delta H of the system and we divide that by whatever our temperature is. And we need to remember to convert our temperature into Kelvin. So the second law of thermodynamics, basically, so this is what we just saw. The entropy change of the universe is the sum of the entropy change for the system and the surroundings. The second law of thermodynamics states that all spontaneous processes or changes cause an increase in the entropy of the universe. So for a spontaneous reaction, again, delta S must be positive. For a process with a negative delta S of the system, we can make this positive, but what would have to be delta S of the surroundings? That's basically the question. So you can have a negative delta S of your system. So we can have a negative number here, but then we're going to have a positive delta S of the system that's greater than the negative that's on, a positive delta S of the surroundings that's greater than the delta S of the system, because we want this to be a positive number. So you can still have a negative delta S, right? And think back to when we were talking about to determine whether a reaction is spontaneous, you have to consider not only delta S, but also delta H. So we can have a spontaneous system if delta S is negative, but then delta H is going to have to be much greater than delta S. The positive on the delta H is going to have to be greater than the negative that's on the delta S, so that we have a positive delta S of the universe. So again, delta S of the universe has to be greater than 0 for a spontaneous process. If delta S of the universe is less than 0, it's going to be a non-spontaneous process. And if delta S is equal to 0, you have a process that's at equilibrium. So that's all we need to know for the second law of thermodynamics. The third law of thermodynamics deals with perfect crystals. So the entropy of a pure, perfect crystalline substance at 0 Kelvin, again, remember to transfer or to convert your temperature into Kelvin, is 0, right? So the third law states that delta S, or S of a pure, perfect crystalline substance, is equal to 0. And I'll show you what that looks like. But again, we're talking about it has to be at 0 Kelvin, not degrees. So we know that the S of a pure substance at 0 Kelvin is going to be 0. But how do we calculate the entropy of a system that is not pure and perfect? And so this is where we're talking about standard entropy. And so you're going to see these two, and so I want you to know what that means. If you just see S, we're talking about conditions that are outside of standard conditions. So remember, S naught. So whenever you see this symbol here, S naught, that means that you're talking about standard temperature, pressure, right? So 25 degrees Celsius, 1 atmosphere. Whenever you just see S, for example, it just means that those are non-standard conditions. So the temperature can be anything outside of 25 degrees Celsius, right? So I just want you, because you're going to see that for when we get to delta G, you're going to see G and you're going to see G naught. And G naught just means standard conditions. G means whatever conditions they've given you in the problem. But if you see the naught sign, so that's that little degree sign there, just know that that means you need to understand that they want you to calculate it at 25 degrees and 1 atmosphere. So it's possible to determine the entropy of a substance that's not pure. But again, you need to understand standard entropy, that's S naught. And then standard entropy values can be used to calculate the standard entropy for a process. And so that's what we're going to talk about now. So here is table 16.2. And so again, these values have already been predetermined. And so on the test, I'll be giving you the values. When I ask you to calculate delta S or delta G of a system, I'll give you the values of the molecules that are in the reaction. And then you can do the calculation. But notice that the pure substances, right, like pure carbon, has an S value of 0. Pure oxygen, 0. So your pure substances at 0 Kelvin are going to have a delta S value of 0. But here are the delta S values for molecules or compounds that, molecules or atoms or compounds that are not perfect or not pure. So how do we calculate delta S of a non-perfect or non-pure system? It's going to be delta S is equal to the sum of your products minus the sum of your reactants. This should look very familiar because we did this a few chapters ago when calculating delta H. So you're going to use the same thing. It's the sum of your products minus the sum of your reactants. And remember to include your coefficients when you are solving for delta S of the system or delta H. You're including the products. The coefficients. So here's a problem. And again, recitation worksheet 11 and 12. Practice those. I'll try to do a tutorial on 11 and 12. Recitations 11 and 12 so you know how to solve. But basically, how do you calculate the standard entropy change for the following process? And so if you go back to this chart here, we know that, so it's asking us to convert from, H2O gas. We're calculating the entropy change for H2O gas to H2O liquid. And so we know that we're going to have to go back to this chart here and look at the values of H2O gas and H2O liquid, the entropy. And so if you look in the red on the right, those are the values of our gas and liquid phases, right? So 188.71 and 69.91. So then all we did here is, remember, delta S is going to be the sum of your products minus the sum of your reactants. So delta S of our product was 70. And then we're subtracting that from 188.8, which is our reactant. And so you get a value of 118.8 joules per Kelvin. All right, so remember, it's the sum of your products minus the sum of your reactant. And so the value of delta S is negative, and what can we tell about that process? If you have a negative delta S, it means that you're going from something that was free to something that is now more restricted. So look at the phase. You're going from gaseous phase to a liquid phase, right? So we're going from molecules moving randomly to now them being a little bit more restricted. And so we expect that delta S is negative because we're losing that randomness. All right. And so again, just to make sure, so you should now be able to state and explain the second and third laws of thermodynamics and know how to calculate entropy changes for phase transitions and